Swayam Prabha. Digital India. Educated India.
We are discussing carbon capture and storage. So we're not talking about his car. He will come in, and when he does, let's give him a round of applause when he does come in. But at the moment, we're continuing the conversation from yesterday, right? So we are in the carbon capture and sequestration, and we said that there are a couple of topics we want to cover, and among those were storage options. What storage capacity do we have? And we'll discuss when we go into geologic sequestration, how do you calculate storage capacity and so on. What we'll cover today is monitor, verify, and assess. How do you monitor? But this will be more broad because we are not talking about in-depth calculations for geologic storage. Just for your information, this is my team. Out here are the equipment. As you can see, some of them home built, some of them bought. Actually, there are two equipment in my lab that are bought. The rest are all home built. They're built by students like these. These are 2 Indian visiting scholars. These are this year's batch of students. These 2 are PhD students. And she's senior's PhD. She's about to complete about 1 year to go. And these are new students deciding what they want to do in their program. I direct the center. Louis Serpa is a co-director. Wei Ping Wong is our technician. He's the one who makes magic work. Jyoti Behura used to lead this team. There were 3 of us. Jyoti has since moved on and formed his own seismic interpretation company, seismic imaging company. We still collaborate. Jyoti is on the thesis committee for Maureen, for Dorothy, and for Mario. Most probably he will be on Joseph's thesis committee as well. So that's who we are. Okay, let's go back to storage. Oh, of these, Dorothy is looking at CCS projects for a project in a storage characterization project in Japan. Maureen is developing methods to do seal integrity, diffusion coefficients into seal rocks. Mario, as soon as that thing comes up, Mario is working on basalt mineralization. Mark is deciding whether he wants to work on basalt mineralization or feldspar mineralization. He's deciding between Mario and Dorothy. Right now, Mario is winning. Joseph will work on imaging and full waveform inversion. Ali Al-Muallim is working on machine learning for full waveform inversion. Benny, Iraf, they are still deciding what they want to do. So that's sort of the composition at the moment. These are all my students. Louis graduated all of his students. He has not gotten any new ones. He is looking for new ones, and he should get a whole spate of new ones in the spring, which means that we will double the size here. Anyway, okay, so as you can see, most of my group works on carbon sequestration, both experimental work as well as theoretical work. And then a big part of our effort is on machine learning. Maureen, Ali, oh, I forgot a postdoc. We have a postdoc and I forgot to list him, but he's the one who's leading the machine learning efforts on both well log interpretation as well as image processing, digital rocks. So we were looking at different ways to store, what the options are, and we said that we have EOR processes where we are injecting carbon dioxide, producing more oil and gas. This is offshore, this is onshore. We also have offshore saline aquifers where the salinity of these formations is much too large, and so it's not potable water and we can inject in these. The third aspect was unminable coal beds, where we were investigating and exploiting the preferential affinity of coal to carbon dioxide over methane. All of these allow us to have a couple of different options. One is utilization, and I think we stopped over here. We were talking of geothermal applications. So that is in the utilization part. We can use carbon dioxide to get more oil, more gas, more energy. And in that process, we lose about 30 to 40% carbon dioxide that's left in the subsurface. So sometimes we will count that as storage. And we'll discuss this a little bit more, why you should and shouldn't do that. But the fact remains there are long-term, 20, 30 years projects that are underway that have effectively stored millions of tons of carbon dioxide over the 30 years. So the prime example that we look at is Weyburn. That's an oil producing field in Canada that has been injecting carbon dioxide to produce more oil for the last 20 years. So that's the utilization part. And then we have primary storage, storage for storage's sake. And that is in depleted and marginal oil and gas reservoirs, where it does not make economic sense to produce more out of it. Either it doesn't flow or it's much too costly. The oil is not of good enough quality. So that's the injection in depleted and marginal reservoirs. We have injection in coal seams, deep saline aquifers. And then the other part here is the reactive formations, where we can put carbon dioxide in formations that will react and hold carbon dioxide in place. It mineralizes. So the advantages of these two, of going to reactive formation, is that once the formation reacts the carbon dioxide completely, we do not need to monitor anymore. Once you can prove most of the carbon dioxide, 90%, 95%, has reacted, and the rest is not going to move because it's trapped as solubility trapping or some other type of trapping, you can declare success and be relieved of the requirement to monitor. All of these require long-term monitoring to ensure that the carbon dioxide is staying where you modeled it to stay. It's not migrating into other formations or migrating upwards into your groundwater or into the atmosphere. Another part which is really interesting, and you heard Professor Dalia talk about it. Dalia's last name? Naidu. Yes, Naidu. Arnapalli. Yes. So he talked about it. He talked about the swelling properties of clay with carbon dioxide. So if we're doing that, if we have clay minerals, and I can assure you, wherever you are, you will have clay minerals. So if you have clay minerals in the subsurface and you're putting in carbon dioxide, those clay minerals will swell. You can get excess stress that could be over and above the strength of the rock, which means your rocks will fracture. So that's one of the consequences which you need to account for, which you need to monitor. Your pressure and stress conditions need to be carefully monitored. The other part is, if you think of a reservoir, we have a large basin, and you can think of Saurashtra, for example, prime location to sequester carbon dioxide. And there are 3 or 4 different projects far away from each other, but it's in the same basin. If it's in the same basin, the stresses will be shared. And so it doesn't matter that you are 100 kilometers away from the next basin, the next project. Projects are far enough separated. They might have separate hydraulic properties. Storage might be local, but the stresses will not be local. So what we are moving towards now is to say, yes, there is a project-wide stress mapping that needs to happen, but there should be an oversight authority. In the case of India, it would be DGH, or it could be one of the DGH. Who else monitors? Is it DST? Would DST be? No, MOE, Ministry of Earth Science, right? MOES. So either DGH, Department of Division of Hydrocarbons, Directorate of Hydrocarbons, right? DGH, or it would be MOES, Ministry of Oil and Ministry of Earth Sciences. They would be the monitoring authority that have jurisdiction over the entire basin. So what you're doing is you're saying, we are perturbing, and we will perturb the stress field regardless of what we do. And we are in this room is our basin where the water is there. That's one project. Here's another project, and there's one project in the middle. What we are starting to recognize is these projects are isolated in their storage chambers. The extent of the carbon dioxide as it migrates outward doesn't encroach on each other, but the stresses are shared within the basin. It's one stress field. If I perturb here, I will change the stresses in the other 2 places. And so we are now promoting and requesting the Department of Energy in the US to change their thinking, to change their approach to say someone needs to track how many projects are there in one basin, and there needs to be either a consortium of projects that share stress data. Otherwise, 50 years from now, 30 years from now, each one will have injected 50 million tons. So the basin cumulatively has 150 million tons of carbon dioxide with local stress changes that are then being shared between the 3 projects. The overall stress in the basin is something that needs to be managed. We don't manage that enough today. And we'll look at some of those factors of what is impeding the progress of CCS in to be much more than what the promise is. Remember, we looked at data that said there are thousands of gigatons of carbon dioxide storage capacity that's available geologically. So why don't we all do it, right? So that's the part which we are looking at to say, okay, what's stopping us? What are the roadblocks and what are the solutions against that? Okay, so what happens? We inject carbon dioxide in the subsurface, and once it's injected, there are flow and mobility mechanisms that control how far it will spread. So if you think of this is my surface. I have a well that I have drilled here. and this is my target, and this is all the seal above. When we inject carbon dioxide, we hope that it will go in, or it does go in, because we put excess pressure. So we have carbon dioxide that's going in and going into the reservoir, because we have excess pressure that's pushing carbon dioxide away. The flow and the transport, permeability in this formation, fluid permeability in the formation, pressure, viscosity, and heterogeneity or fluid anisotropy, both of them, texture, will guide how these will flow. So the fluid flow responds to my fluid pressure gradient. So we have pressure gradient that the flow here responds to, that's the dP. It responds to natural hydraulic gradients that might be present. Buoyancy will guide, that's a difference in density between the formation fluids and carbon dioxide. There will be diffusion processes. All of these, we normally think of carbon dioxide going out as a uniform phase. That really does not happen. What we are observing is it almost forms fingers where you have channels where it flows preferentially, others where it doesn't go in. And that can be due to changes in flow properties of the rock. You have higher and lower permeability. You have larger and smaller pore throats. So there is an impediment for carbon dioxide to enter. And so all of that will give us a dispersion and a fingering effect. This becomes a little bit more problematic because imaging it with geophysical methods is now not easy, because if it is fingering, we have a commingled response of areas that contain the original fluid and areas that contain the new fluid, and a mixture of those. We will have dissolution into the formation fluid. Carbon dioxide, depending on the type of fluid, dissolves to different extents. You have more or less dissolution. We will have mineralization, regardless of how unreactive the formation is. We will have some mineralization either with the clay minerals or with the feldspars, plagioclase, siderite, or any lithic fragments that might be present. And finally, if we have organic matter, carbon dioxide will absorb into the organic matter. So there was a thrust to use then organic rich shales as a target to reverse process the unconventional oil and gas production into an unconventional carbon dioxide storage, mainly because of the very large storage capacity that we know exists within the organic matter. It still remains on a research level because this is a very slow process. Permeability is very low, so getting it into the shale, getting carbon dioxide into the shale is a challenge. Okay, so the primary ways in which we can trap carbon dioxide. Remember, we're trying to trap. We don't want it to flow forever because then it's uncontrolled. So we model. We say we are going to inject over here, and we model and say that the carbon dioxide will eventually occupy this much of a space, which means we have to image it, right? We have to follow up. If we have 30, 50 years of imaging requirement, we will need to image this entire thing and show and prove that our models match reality. So, when we are looking at the trapping contributions, there are 4 main mechanisms. We have structural trapping, residual carbon dioxide trapping, solubility, and mineral trapping. And this is an early, about 20 years ago, a paper put out by Sally Benson and her postdoc, Ben Cole. And they put in storage security on this, and they said these processes, some of them happen immediately, others take tens of years, hundreds of years, and mineral trapping would take thousands to tens of thousands of years. Let's first look at what these processes are. So, if we're looking at structural trapping and stratigraphic trapping, we're looking at geologic structures that prevent carbon dioxide to moving out. So, that would be something like this. You have a structure here, a fault. This is carbon dioxide injected over here. This is a sealing fault. Carbon dioxide will occupy in this space, cannot move any further. That forms a natural seal. In this case, this is a seal here from the structure here. We have an anticline. We're injecting carbon dioxide here. That structure prevents carbon dioxide from going anywhere else, and you have the seal above that doesn't allow carbon dioxide to move up and down. Lateral movement is prevented by the structure. So that's what we mean when we say structural trapping. This happens pretty much right away. We look for things like this. We look for anticlines. We look for sealing faults so that we can have that part. Storage security is as good as the structural trap. If the fault is a sealing fault and carbon dioxide dissolves the sealing material, usually the sealing material is calcite. If you put carbon dioxide mixed with water, that acid will start to dissolve the calcite. And so your sealing fault, which you thought was a trap, is not a trap anymore. So that's the part which we look at over here. That's structural and stratigraphic trapping. We can also see residual trapping. We saw this yesterday when we were looking at the oil wet and water wet systems. When you had excess of one fluid, that would effectively trap the other fluid. And so that is something like this. This is our place for carbon dioxide. Here is the flow that's happening for carbon dioxide, but we leave behind pockets of carbon dioxide that don't have enough pressure differential to move. There is nothing that's promoting movement here. There is enough pressure differential to get carbon dioxide to move. This one is trapped. Very much like bypassed oil. We have the exact same thing where some parts, in many cases, all of the oil or carbon dioxide, if it's occupying these spaces, will not move, will be trapped. Your primary flow happens in the center of the conduit here. And so we have residual trapping, the residual trapping in the pore fluid. We also have solubility trapping, and this is when carbon dioxide dissolves in brine. Whenever you put carbon dioxide into say an aquifer, the carbon dioxide will dissolve in brine, brine will dissolve in carbon dioxide. You get this bi-directional dissolutions. That part will stay if your pressure and temperatures are constant, which they mostly are. And the final one is mineral trapping, when you have reactions happening. So that's the four methods of of trapping that we can expect to find in the subsurface? Yes. Sorry? Oh, yeah, sure. The question is if I can explain the formation of structural trapping, right? So imagine if you I'm just looking for a space. Okay. Think of okay. I have my boarding passes. So normally all your deposition is happening on a flat plane like this. Everything's being deposited. Even if it's this way, it's sort of pretty benign this way, right? Now, if you think of plates acting or some fault, some tectonic activity, that's going to compress and push this up, right? So now you have this sort of this is what we call an anticline. So if you inject something here, you have to have very high pressure for it to move down dip, right? So it will stay here, and you make use of the density contrast between the injected fluid and the existing fluid. So that's one way of trapping, right? The other one is, if you think of something like this, there is a fault in the middle, and if this fault is sealing, it might be at a dip here, this fault is sealing, everything comes up dip and stays in place. Yeah. Yes. So if your fault is sealed with so the question is there a reversibility in the fault?
There is a formation for the fault.
Yeah.
And after the storage of CO2, if the fault is reversible, means the CO2 can escape.
Yes, yes, and that is a distinct possibility. If you have a fault that is sealed, you want to first investigate what the sealing material is and what is the dissolution potential of the sealing material so that you don't open it up over time. Yes, indeed. So if you have very soluble minerals that are sealing, you would want to go further away, or you would want to treat faults. So there are schemes and methods that you can do microbially induced calcite cements, what's MICP, and that is injected into, this is still in the research phase, but you inject it, the concept is you inject it in the fault and you get microbes to form a seal and fill up the fault so that it doesn't flow anymore through the fault. So there are ways to do that, but it's an expense again. So you rather have something that you can avoid. So when we'll look at some seismic data next week from the storage site that we are targeting, and you can see that there is one big fault and we are saying we want to drill away from it, so we're not going close to it. You want to avoid these cases. In many cases, you could have a sealing material that is not calcite but dolomite. Dolomite does not dissolve as easily, right? So those are some of the considerations. Or you could have quartz. In many cases, you have veins with quartz filling the veins. So those might be a very nice way to exploit the fact that there is not a soluble mineral present, right? So there are ways to do that. Yeah.
Just explain the seal, about the seal rock. If you see,
I see. I misunderstood the question completely. Okay. Yes. So, if there was no fault, right, then I can draw it here. Then this formation and that formation would be connected. Right now what's happened is there's a fault and there's slip, right? So if there is no slip, then this would continue through, and so there is a continuity even across the fault. When it goes through, you have flow. This is a seal, this is a seal. These are seal rocks. Nothing is going to go up here or down here. With this movement, there is uplift here, down throw here. So what happens is this formation now abuts against something where it cannot flow, right? So that's the part which is very interesting. Thank you for clarifying. I was not understanding your question. So now it will not flow because this thing is here that's preventing flow. In that case, there are two possibilities. One, carbon dioxide will either stay here, not move, or it will go along this fault. That's the part I was talking about, that these usually have some material that is sealing, which then has a seal over here to prevent it from going outside. And over here we have the natural seal because it has now moved to get the permeable seal against the permeable rock against a seal. Good? Okay.
Ma'am, I also have a question.
Yes.
So generally we have seen that along the fault lines, we have the major disturbances because of the tectonic movements, and a lot of seismic activities takes place along the fault line. So like once a fault has been created and it has been sealed, there is a possibility that in the long run, there will be disturbances along the faults and there will be change in the, placement of those ceilings.
Yeah.
So at that circumstances, our carbon dioxide might leak. So
Yes. So that happens. So this sort of a scenario happens if there are stresses that are acting here, right? You have stresses that are pushing things together. Rocks break and move when the strength is overcome by excess stress. So when we map stresses, if the stress is equal in every direction, it can be very high, but the rock is not going to move. The movement happens when these stresses are larger than these. So that when you're pressing this together, it breaks and one part moves up, the other part moves down. It's a little bit more complex than that, but think of it in a way where you are pressing things together. If you're pressing equally in every direction, it's not going to break. That will depend on the compressibility. It will break if you overcome the overall stiffness, but it will not move. For something to slide past one another, you need one set of stresses that are larger than the other set of stresses. We can measure those. So part of the study that has to be done before you select anything like this is to say, are the stresses equal? If they're equal, how much are we going to perturb the system? If it is isotropic, then the stress will be perturbed in the same way, which means the stress should remain isotropic. If you have anisotropy, you can start with equal stresses in every direction, but now your anisotropy will put fluid pressure in one direction more than the other, and now you have anisotropic stresses, and then you need to be worried about rocks, the fault being reactivated. So fault reactivation is something that happens when you perturb the stress system in a way that stress reinforces the initial stress, and that causes it to start moving again. Look, so you need to know what the initial stress is, and you need to model what your stress will be after injection. Plus, you need to have the fracture strength. What is the fracture strength? So those parts are real and they're measurable. You can model them, you can measure them. And that's something that you have to do. If you have fracture, even if you don't have fractures and faults in this area, you still do need to make sure that you don't create faults. So that's the part which needs to happen in the characterization stage when you're planning your project. Not even in the mature stage when you're actually doing everything to look at capacity. This type of analysis of the local stresses, the stress anisotropy, needs to happen before you get too far into the project. Because otherwise, you're right. If you have a fault that it can slip, you have stresses that will be overcome, the project is not going to happen. It's too dangerous. Okay, good. Okay, so this is your solubility trapping, and the mineral trapping is pretty much similar. Here you have reactive surfaces and you have bicarbonate here, and you're forming some sort of a carbonate, either calcium carbonate or magnesium carbonate or a mixture of those. Okay. Now, one of the things which many of us have gone back and said this really is not correct because it's misrepresenting from lab studies that came out that already existed by Adams et al. And then subsequently by many other people, including Falcon Suarez, where they showed that this mineral trapping occurs within weeks, if not days. So, and this has been done with imaging while you're injecting carbon dioxide and showing, demonstrating, visibly demonstrating the minerals being formed due to carbon dioxide and brine. And now, of course, it's a major project in Iceland where they are doing mineral trapping almost on a daily basis, and they're showing results of that happening continuously. So this needs to be moved. So the part which, the reason I bring this up is to say that in 2002, we were beginning to see changes like this. In 2005, they were overestimating. We go back and revise and revise. That's how science works. You do something, it doesn't mean that they didn't know. It just means we know more now. We have more data now, right? So that part, and this is really holds a lot of promise because there are large igneous provinces, reactive rock provinces that exist in many parts of the world. In some cases, it is more interesting for nations with big basaltic provinces like Iceland has made a business case out of it, India, Brazil, and parts of US where you have, yes, the Wallula project, yep. You have the Columbia River basalts where you can get mineral trapping on a very nice large scale. So you don't have to worry about long-term monitoring, long-term processes. Mineral trapping now is also gone further than that to be using it for in cement processes as well as in other mining processes so that you can trap carbon dioxide in waste products. As you trap it in waste products, you make something more out of it. So there's a whole field of research that's doing studies in mine tailings. Those are mine waste products that are brought out. And in the process of mining, you get the ore you want, but you have a lot of rock fragment. So it's already broken up, which means a lot of reactive surface has been exposed. And so there is the concept of injecting carbon dioxide in mine tailings and creating building blocks that might not be very strong, but they can work very well for retaining walls, for example. So low quality building blocks are possible to use with mine tailings. So there is a much bigger potential for mineral trapping than what we are looking at today. In this case, this is estimates. Most probably these need to be revised, these need to be locally refined. We have a lot of information, local information. The challenge is when you do something globally, you examine global capacity, often it's conditioned by what you know. So if you're based in Europe, you will have a European point of view, and then you will examine everything through that lens. It's very useful for every country or every continent to define their own capacity for carbon dioxide storage. That, I think, is a big challenge. I have not seen a map, a sedimentary basin map of India. I have not seen a storage capacity map for India. And that would be very useful if someone were to take it up. I say to every university I go, in the hope that one of the students will catch it and say, okay, this is going to be my project from now onwards. The part which is interesting in this case is a concept of data sharing. You need data from many different basins. Those data are sometimes not as available. But if this were made available, that would be really very useful. Okay, so what is the geologic sequestration project or process? How do we do it? We first need to identify, this is for the US, it's complex and there are too many colors here, but if you think of all colors on the worm scale, these are emitters. So you have cement, steel, and steel here. Blue and gray are power plants, and the black dots or the size of the dots show you how much they emit. And so you're first counting up, where do you have the emitters? That's critical, because I don't want to have a storage site here where I will need to bring in carbon dioxide from further away. If I have a set of large emitters here, for example, I would want something in these two states. If you see over here, as usual, as normal, coastal regions have very large populations, have a lot of industry happening to support that population, and US in this case was populated from the east over to the west because there's a big mountain range in the middle. And so there is a lot of emitters here, and then you have California out here, Washington out here. So when we're looking at storage, this is Colorado. I was invited by the Osage tribe in the US to present what the possibilities would be for their tribe in Oklahoma. And if you look at this in Oklahoma, a lot of Osage tribe members have oil fields with refineries in the region. So, and they have a lot of natural gas power plants and coal-fired power plants. So it makes a lot of sense for the tribe to be putting a storage facility here. For Colorado, there is the corridor from Colorado Springs, Denver, and Fort Collins. So you have emitters all along here. There are oil fields, there are oil refineries. So this makes sense for us to have things here. These here are cement factories and steel plants. Our project is right next to the cement factory and the steel plant, just because we don't want to have to truck things in or pipe things in from far away. So that's the first step. Where do you have source of carbon dioxide? How are you going to bring it to the location? Once you have that, you identify your basin. So in this case, for Colorado, we have the Denver-Julesburg basin that extends quite a bit on this part here. So that's what we're making use of. So you identify the basin and you divide it up into sub-basins and say, okay, here are potential areas where we could have storage. Once you have that, you look at all the information you can get. This information would be subsurface information, would be facilities and emitting information, would be information for workforce. Do you have people who you can employ, local talent, or do you have to bring people from the outside? Once you've done that, you sub-select based on geology, based on availability of carbon dioxide, based on facilities that might already exist, and you have a couple of selected areas. Within the area, let's say this is my site that I've selected. I go in here and have potential sites where I will do in-depth characterization. This is the part where now I start drilling wells. And I say I will take these three and drill 3 wells, 1, 2, and 3. In this case, sometimes I will need seismic data. How many of you have heard about seismic data? A few. Okay, we'll when we talk about geologic sequestration, we'll look at seismic data. Think of it as sonogram. You go to a doctor, you get a sonogram done. It's a sonogram of the earth. In a simple way. I know he's cringing, but that's pretty much it. You have a source that's giving vibrations, and you have sensors that are picking up. Sensors being our ears. Think of my voice being the source, your ears being the geophones. That's what we're doing, right? So we would have some sort of seismic information that tells us what the substructure looks like. That's where we map the faults. That's where we map what the traps are, the structural traps. Once we have that, we locate our wells, we drill wells in these potential sites. Once that is drilled, that's the site characterization. You characterize the sites of these, then you pick out which are the qualified sites that you can prepare and get ready for permitting. All of this needs to happen before you apply for a permit to inject carbon dioxide in the subsurface. What is the process here in India? If you were to, let's say if I want to develop a project, we back to IIT Madras, right? I want to drill a well in your football field. What permissions do I need? Clearance by the environmental board, right? So for clearance from the environmental board, that will look through everything that I've prepared, which means I need to tell them what the source is, I need to tell them what the sink is, I need to tell them what the seal is, I need to tell them the long-term prognosis and what I will do to monitor and prove to them that my seal is holding and it's not moving, and I will need a mitigation plan. If something starts to move before it comes to leak, an actual leak, or before it comes to a movement of the fault, what will I do? Will I back out the pressure? Will I remove the carbon dioxide in an alternative place? Or if I have a spill, what are the alarm systems? If I'm damaging structures because there is subsidence, some countries require an extra fund to be created out of which you will pay damages. That is the permitting process. Once you have the permit from the environmental board, in the US it's also the environmental board, the Environmental Protection Agency, they are the ones who hand out the permit and say, okay, you're good to get that. I will still need to buy the land or lease the land, right? That is on another page. That has nothing to do with the permission to do it. Just because you have permission doesn't mean you can do it, because you might not have the land lease. Yes, you need money. Yes, in all of this we need money. We need someone over here. We need someone to pay for the analysis here, right? This is investment. This investment needs to happen. That means I need to be able to buy data to examine. I need to be able to drill wells. This is all upfront money. I need to be able to drill wells. Drilling wells is not enough. Now you're bringing out data, you're bringing out cores. Someone needs to make the measurements. Someone needs to analyze and prepare all the sites. Once you have that, you need to prepare the permits. You need to have all of that plan in place. And then you need someone to give you money to lease the land and do everything in place. So that's sort of the part that is needed. Up until here, you've already invested about $30 million for 1 or 2 wells. So that's the part which we investigate when we talk about drilling a site. Now the actual cost might be different depending on which country, which locality you're in. If you're competing right now, if oil and gas is in big demand, you're competing for drill rigs with oil companies. They have deeper pockets. They will always win. So we are then left at the mercy of when they don't need the rig is when it comes out to my site to drill a well for me. So that part becomes a challenging thing. We have a couple more minutes, so let me just finish this part. So what are the critical steps? This everything that we talked about right now. We need to locate and characterize the potential sites for large-scale storage. It's not enough. Remember, we've said you're investing millions of dollars. You don't want to be putting in a small amount and then you're done, because then the investment is not worth the revenue you will make from tax benefits. So you need adequate thickness, you need extent, you need porosity, and you need fluid mobility. These are the 3 main things that you need. You need saline, if it's salinity driven, or if it's aquifers, the salinity will have to be proved to be above a certain standard. Varies from country to country. These are the different types of targets that you will need to locate and identify. Once you've done that, you will need to manage and quantify the storage resource. We've all decided on, agreed on a standard that's driven from the Society of Petroleum Engineers. They had a reservoir resource management guide, and that's now adapted for carbon storage, SRMS. That's the Storage Resource Management Guide. You follow that. So you say, what fraction of the pore space is available? How much of the pore space can we use? Either pressure up, so that's your pressure, and solubility, that will depend on what fluids are present. We also need the capacity and injectivity. How much can you inject? You don't want to inject at such a high rate and pressure that you're fracturing all the rocks on the way. So how much can we inject? How fast, how much can we inject? Every day that's spent at the rig costs money. So you want to be injecting at the rate that the formation allows, not too less, not too much. So that's the injectivity. How much pressure can we use for injection? How much can we store? And the big thing here is, how far will it travel? From one injection site, given the pressure differential that I can put in, how far will this carbon dioxide go? Right? And then what is the safety? What is the seal integrity? What will prevent carbon dioxide from entering the upper layers or the lateral seal layers? Can it move in any other place where we do not want it to go? Fractures, cracks along the wellbore. This is a very big challenge. The wellbore, we'll look at design of wellbores on Monday on how things can leak along the wellbore. Will the carbon dioxide injected indirectly through stress changes cause the formation to break and produce earthquakes? So induced seismicity is something people worry about because we have seen it a lot through injections of wastewater. And if we're storing at large depths, how deep is the formation? How far must we go? We want to optimize it. We do not want to have too much pressure to inject if it's very deep. If it's very shallow, then there is more of a danger for it to come up. Most of the times, carbon dioxide at the pressure temperature in the subsurface will exist in supercritical state. We want to be far away from groundwater, at least 1,000 meters away, 1 kilometer away, if not more. And we want to make sure that we have sensors in place to prevent likelihood of any contamination.